Hello. So today's video, cylinders and quadratic surfaces, as well as vector functions and space curves. That's a lot of big words, but let's go ahead and break them down. So a cylinder, the definition that we'll be using for this class, a cylinder, it is a surface that consists of lines that are parallel to a given line that also pass through a given plane curve. So the plane curve can be just about anything. You do know the basic cylinder. It goes around in a circle. All the lines that are going up and down are parallel with each other. In this situation, they'd be parallel with the z-axis. So every single line going straight up and down is parallel. If you start going other directions, it gets messy, but all these straight lines are parallel to a given line. What you don't immediately think of as a cylinder is something along the lines of this. So, as you can see, if I draw a line parallel with the y-axis on this graph, wherever I draw it, it's going to be parallel to the y-axis. So by this definition, that is also a cylinder. So the basic way to keep in track if something is going to be a calculus cylinder is if it doesn't matter what one of your variables is. That's the simple case. Sometimes it gets a lot more complicated than that. But for now, keep in mind that if one of your variables is not in your equation, so like in class back on the first day, you had an equation for a circle. Well, the z was not in it, therefore it would end up causing a cylinder. So it will always end up happening if one of your variables is completely left out, that's going to end up causing a cylinder. Now, quadric surfaces can be slightly more complicated. So what is a quadric surface? Well, a quadric surface is essentially any second degree function which has this type of form. This looks big and ugly. Basically, it means it has your variables to the second power and interaction amongst your variables. At max 2 variables at a time. Quadrics comes from quadratic, which means 2. So it's a situation where only 2 variables can interact at once at any given time. Therefore, you end up with this equation. Most of the time, you're not going to end up having all these variables. And sometimes it's going to come out and look a lot nicer than what this does. So it's just one of those types of surfaces that you have to keep in mind. If you see it in this form, it's a quadric surface. Now, basic ways to visualize surfaces in 3 dimensions based off of equations. The very best way to try and do it is to take your equation, set one of your variables equal to some value, it doesn't matter what, and then graph it for that cut. So you're slicing it and just drawing 2-dimensional shapes. And you can always do that. Do it the first time. If you're doing it with z, set z equal to 0. Cut, graph that. Then set z equal to 1. Cut, graph that. And then you can essentially stack them on top of each other, and you can create this type of image over here. This is a lot of ways how MRI scans and other things create 3-dimensional images. It takes a slice at a time and moves on to the next slice. Now, here are some examples of what some of the quadric functions look like. So if you notice these equations and these types of forms, you can identify what type of things these are. This should be helpful. This is in your book, so you don't need to write down every single one here. This is just to show you some of the basic ones. But I do suggest going through it and reading through it a couple times and making sure you recognize some of the basic forms. All right, so now let's go ahead and talk about vector functions and space curves. These are going to be used fairly often throughout Calc 3. So a vector function, well, it is a function whose domain is a set of real numbers. Usually it's going to be of the form like t is from here to here or something. And its range is a set of vectors. So whenever you put in a real number, you will get a vector back out. But the vectors have to be written away such that each component of the vector is a function of your domain itself. So everything has to be a function for it to be a vector function. And to evaluate this, all you have to do is t, put in for each of those, and there you go. Quick notes about vector functions. Firstly, if you want the limit of your vector function as your variable is approaching a particular value, that's the same as if the limit is approaching that particular value for all of the interior components. So that makes it very easy to deal with computationally. And similarly, your vector function is only continuous at a value a if and only if it is all of its parts are continuous at a. So if one of your components is not continuous at a, the function itself is not continuous at a. Why am I mentioning this? Well, because the definition of a space curve is it's a continuous, real-valued vector function. So it needs to be a vector function, and each of its components has to be real-valued. Eventually, you can get into imaginary and complex stuff. It's not necessary for this level. Now, the advantage of space curves is they will look something like this. Throw two of these together, you now have the double helix from DNA. They are very useful for making diagrams of things you actually want to incorporate or deal with. So we'll be dealing with these a lot. Now this is a space curve. The vector function itself would have vectors originating from the origin, from the 0, 0, 0, out to each individual point on this thing. So it looks a lot messier. When we're dealing with space curves, we're primarily focusing at the end point of each of the vectors.